Hello, this is Professor Kuehn, and welcome back to Introduction to Astronomy at Wisconsin Lutheran College. In this week, what we're going to be studying is the work of Martin Waldseemueller. Martin Waldseemueller was born in 1475 in Wolfenweiler, Germany. He went to the University of Freiburg, and then he became a Catholic cleric and later was ordained a priest. He was a very influential geographer and cartographer, and he made a very famous 12-panel map of the world. And this map is known for giving the name America to the New World after the journeys of Italian explorer Amerigo Vespucci, which had happened a little bit before Martin Waldseemuller's time. This map, which is shown at the top of page 102 in a student's guide to the great physics texts, measures 4 feet by 8 feet when fully assembled. And it was really the first to depict the entire Western Hemisphere as a separate continent between two vast bodies of water, the Atlantic Ocean and the Pacific Ocean. Interestingly, Waldseemuller's later maps omitted the name America, simply referring to this new continent as terra incognita. For those of you who know Latin, that means unknown land. Nonetheless, other famous map makers had already adopted and popularized Waldseemuller's original terminology. So what we're going to be doing is looking at some of the text that accompanied this very famous map. The text is called Waldseemuller's Introduction to Cosmography, and it gives an insight into how astronomy is able to inform map making or cartography. So if last week we were looking at how astronomy can inform calendar making, this week we're looking at how astronomy can inform cartography. If you're interested in this kind of thing, and specifically the history of map making, there's a wonderful book that is called The Fourth Part of the World. And that is a book that tells this fascinating history of this particular map, Martin Waldseemuller's famous map. Interestingly, this map right now is on display in the library at the Thomas Jefferson Building. It's owned by the United States Library of Congress. It was bought in, I think it was 2001, from a Prince Waldburg wolf egg in Germany who had been storing it in some room in his castle in Germany for centuries, or at least for some long period of time. But it was bought by the United States and is now displayed at the U.S. Library of Congress. By the way, why was it called the fourth part of the world? Well, a lot of the maps at the time, depicted the world as comprised of 3 parts or 3 continents. There was sort of the Middle East, or Jerusalem was often depicted at the center, and then off to one diagonal was Europe, off to another diagonal was Asia, and off to the south was Africa. So those were the 3 parts of the world: Europe, Asia, and Africa. And so the New World was then called the fourth part of the world. For those of you who might be kind of curious, I always wondered why, this is a little bit of a tangent, but I always wondered why the Olympic flag shows 5 rings instead of 7 rings. After all, there are 7 continents, right? That's what we've been taught as Americans. Well, I guess that makes sense if you consider North and South America to be separate continents. But most of the world sees the Americas as a single continent, and then there's Europe and Asia and Africa. That makes 4, and then there's Australia and Oceania, which would be 5. Those are the 5 continents that send Olympians to the Olympics. Of course, there's Antarctica too, but there aren't any Olympians from Antarctica. Anyhow, so this week we're going to be looking at the work of Martin Waldseemueller and how and specifically his Introduction to Cosmography, which is in Chapter 9 in the Student's Guide to the Great Physics texts. Now, Martin Waldseemueller begins this Introduction to Cosmography with a preface which is written to, he says, His Majesty Maximilian Caesar Augustus. So what's going on in this preface? Well, first of all, just so you know, Maximilian Caesar Augustus, he was the Holy Roman Emperor at the time of Martin Waldseemueller. He is the Roman Emperor that came after Frederick III and before Charles V. So you might recognize Charles V as being the emperor who was around at the time of the Reformation and Martin Luther. Maximilian was kind of one of the leaders of the Habsburg dynasty. It's interesting in this preface, this serves really 2 purposes. First, as an introduction, and also as a dedication to Maximilian I. So in this chapter, if you look at the preface, which is on the bottom of page 102, he says that it is not only pleasant but also profitable in life to visit many lands and to see the most distant races. So he talks about the benefit of traveling, and he mentions that Plato, the ancient Greek philosopher, and also Apollonius and other philosophers who did a lot of traveling and how much they learned from their traveling. And he has a quote from Boethius, another famous classical author. So it's kind of, you'll notice that in the work of Martin Waldseemueller, This is not only a book on astronomy and cartography, but he sprinkles it quite liberally with poetry and quotes from literature. So that's something some of you may find notable when you look at this. So he mentions that it's very profitable, beneficial, and pleasant to visit distant places, but he also says it's profitable to learn from books. So he talks about how you can use books in order to learn the manners and the customs of different people. And that's very praiseworthy to learn these things. Then he also has a quote from the Odyssey. He mentions that we can learn from books like the Odyssey, written by Homer, and which starts out, "Tell me, O muse, of the man who after the capture of Troy saw the customs and the cities of many men." So after giving this introduction, he then goes on to mention what influences Waldseemueller himself had. And he mentions that he was strongly influenced by the work of Ptolemy from a Greek copy. So you remember when we studied Ptolemy, his Almagest was a book of astronomy, so he was influenced by Ptolemy's Almagest, presumably, but also by Ptolemy's cosmography. He wrote another book on map making. So there are a lot of similarities between what Waldseemueller is doing here and what Ptolemy had done in using astronomy to inform his map making. And he also mentions that he was influenced by the recent 4 voyages of Amerigo Vespucci. So Amerigo Vespucci had recently explored large parts of what came to be known as the New World, and then because of Waldseemueller, came to be known as America. And if you're interested in reading some of these notebooks of Amerigo Vespucci, by the way, we have a copy of this at the Wisconsin Lutheran College library. They're not very long, and they're kind of short little accounts of what he saw when he came to the New World. It's very interesting. Okay, and then finally he mentions that this is dedicated to his protector. He says, "This work I have determined to dedicate to your most sacred majesty, since you are the Lord of the world, feeling certain that I shall accomplish my end and shall be safe from the intrigues of my enemies under your protecting shield as though under that of Achilles, as I know that I have satisfied to some extent at least your majesty's keen judgment in such matters." And then he goes on to say, this is at Saint Dié, where he was a priest, where he was canonized as a priest in the year 1507 after the birth of our Savior. You'll notice these kind of dedications in several of the works that we're going to be studying in the next few weeks. So later on, when we look at Galileo's Starry Messenger, which was written in 1620s, I believe, and he dedicates it to the Medici family, who was his patron and his defender. So he spends a lot of time in his preface praising the people who are not only funding him, but also protecting him from his enemies. Okay, so that's the preface. And now let's look on to the next chapter. He provides an order of treatment. So he's talking about here what he's going to be talking about in his introduction to cosmography. And so he mentions here that he's going to talk about geometry. He's going to start out by talking about geometry to remind us of the kind of terminology that is going to be useful in understanding map making. He's going to talk about the meaning of terms such as sphere and axis and poles. He's going to talk about the circles in the heavens. Remember, the heavens, we mean the celestial sphere that is orbiting around the Earth. And then he's going to talk about how you divide this sphere up into degrees. He's going to talk about the various zones. He's going to talk about parallels, which came to be known later on as latitudes. And then he's going to talk about the winds and the directions the winds come from, and then how the Earth can be divided. So basically from about point 1 through 7 is in chapter 9 in the student's guide, and points 8 and 9 are discussed in chapter 10. We may not get to chapter 10, but we're definitely going to spend time on the first 7 points here, which are in chapter 9. Okay, and then he mentions at the end of this section on order of treatment that he is going to attach to this introduction to cosmography the 4 voyages of Amerigo Vespucci, his notebooks. I have not included these in the textbook, but like I said, if you're interested in those, you might check those out at the Wisconsin Lutheran College Library. Okay, now let's move on to his chapter 1. Chapter 1 is a review. This is on page 104 in a student's guide to the great physics texts. Chapter 1 is the principles of geometry necessary to an understanding of the sphere. So I'm going to spend a few minutes going through this because it might have been a little while since some of you have taken a geometry course. And there's nothing really that complicated here. He's just reminding us of some terminology in geometry. So he mentions that a circle is a plane figure bounded by a line drawn around it, and in the middle there's a point. All straight lines drawn from which to the surrounding line are equal to one another. So you can think about this as the definition of a circle. If you draw that line just right, then any line you draw from the central point out to that line is going to have the same length. Those are radii, if you like that term. And so that's just what he means by a circle. Okay? He says a plane figure is a figure no point of which rises above or falls below the lines that bound it. So if you imagine a plane like this, there are 4 lines that bound it. I'm going to draw it kind of thick to just give it some perspective. Of course, it should be very, very thin, in fact, infinitely thin if it's truly a plane. But every point on this lies in the plane. There are no points on this plane that rise above these 4 lines that bound the plane. So that's what he means by a plane. He talked about a circumference as a line that bounds a circle, that all straight lines drawn from the center to the circumference are equal to one another. And then he reminds us of some of the Latin terms, this line right around here, the circumference. He mentioned the center of the circle is a point situated so that all straight lines drawn from it to the line bounding the circle are equal to one another. Some of these you might see as redundant. He mentions what he means by semicircle is a plane figure bounded by the diameter of the circle and 1/2 of the circumference, right? So if you draw a line right here, that's the diameter, and then 1/2 of the circumference, that would be a semicircle. He mentioned the diameter of a circle is a straight line passing through the center of the circle and extending in both directions all the way to the circumference. He says a straight line is the shortest distance between 2 points. So, if you have 2 points, one here and one here, this of course is not a straight line because it's not the shortest distance. So he's describing a straight line in terms of distances between 2 points. He says an angle is a mutual coming together of 2 lines. So if you have 2 lines like that, then what's going to happen is that's going to form some angles here, 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 and here. So he's reminding us what he means by angle. And then he says a right angle is an angle formed by one line falling upon another line and making 2 angles on either side that are equal to each other. So you see here, these 2 angles, the one on this side and the one on this side, are not equal to each other. But if we were to make 2 lines cross in such a way that these 2 angles are equal to one another, well, then we call those right angles. He says an obtuse angle is an angle that is greater than a right angle, and an acute angle is one less than a right angle. He says that a solid body is measured by length, breadth, and height. You might say that it has 3 dimensions as opposed to 2 dimensions, which would be a surface or a plane, and 1 dimension, which would be a line. The next thing that he does is talk about how you measure angles. He talks about degrees, minutes, seconds, and thirds. So it's good to keep in mind here that when we use the term minutes and seconds nowadays, we typically refer to time. But these were not referring to time for much of history. These were referring to angles. Just as a degree is a measurement of an angle, so too is a minute and a second and a third. This is really inherited from ancient Babylonian mathematics and astronomy. They would use a base 60 system of dividing angles. So you have degrees, let's say, and then you break a degree into 60 parts, and each part of a degree is a minute. And then you break a minute into 60 parts, and each part is 1 second. And you break a second into 60 parts, and each part is a third. And you break a third, for that matter, into 60 parts. Each part is a fourth, and so on. Later on, these smaller divisions of angles came to be used to measure time. But at least originally, they were used to measure angles. So there's a close connection between angular measurements and time measurements that arose historically, largely because time is essentially measured by the motion of the sun through the sky. That's how sundials work, and that's how people started associating angles with time.